Alright guys, there was some microphone issues, so hopefully we can just pick up where we left off. Alright, so we were talking about endothermic and exothermic reactions. So ice melting is an endothermic process. Okay, this is an example of a campfire. So in a campfire, the heat is moving from the inside, from the fire, to the outside, right? When you're around a campfire, you can feel the heat, so the heat is moving out. So it's moving from the system into the surroundings, so we call this exothermic. Okay, so those are the two processes involving heat transfer. Okay, let's talk a little bit about heat. Let's see, let me zoom last so you can see the whole page. There we go. So heat is a measure of flow of energy from one object or a substance to another. Thermal energy typically flows from a warm material to a cold material. Generally, when thermal energy is transferred to a material, the motion of its particles okay, let me read this again. Generally, when thermal energy is transferred to a material, the motion of its particles reach thermal equilibrium. So eventually, when a warm material touches a cold material, if you allow it to happen for long enough, they will reach thermal equilibrium. In other words, they're going to start moving at the same speed. In the previous unit, it's not previous units, previous lesson, okay, that was the calorimetry. We studied that heat absorbed or heat release can be measured. The amount of heat flow depends on mass. Okay, so the amount of substance that's present. It depends on temperature. Or actually, temperature is right here. Temperature change. So you measure the temperature change between the before and after process, right? And it also depends on, they call it specific heat. Specific heat is the amount of heat necessary to raise the temperature by 1 Celsius using 1 gram. Okay, so it's just what makes up that substance. Each substance is going to absorb heat differently, and this variable kind of just shows that each substance is unique. So pretty much just to show the substance are unique and they're going to interact with heat differently. Okay, there's a table with the specific heat of all substances, pretty much almost all substances. So we pretty much have to find out what they are and just plug it in. And then in a lab, we would measure the mass and the change in temperature. Alright, so we're going to move into, so the notes are pretty easy to just follow along using a computer and just typing in the words. However, the models are going to be trickier. So what I suggest here is that you just take a piece of paper and actually follow along with the paper, because even though it's possible, it's a little more challenging to do it using a computer. Because I'm going to show how to do the models. Few things to keep in mind. When you're creating a model for heat transfer, that's what it is. And we froze again. Give me 1 second. Okay, so when we're doing models for heat transfer, a few things to keep in mind. We need to draw particles for the model depending on the type of substance. So you cannot draw a model for a solid the same way you draw for a gas. Because what makes a gas and a liquid and a solid different is the space between them. Right, so if you're going to draw a solid, you draw them kind of close together. Okay, so this is just an example of a solid. Okay. If I'm going to draw a liquid, I would space them out. And if it was a gas, it would be all over the place, because we know that gas takes the entire space of the container, right? We know the solid stays in one place, a liquid spreads out, and a gas takes the entire volume. So the second thing that we need to think about is we need, especially for heat transfer, and it froze again. Sorry folks, the document camera keeps freezing. So the second thing that we need to think about is that we need to use arrows to indicate direction and strength of a movement. We call these vectors, but you can just call them arrows. The other thing that you need to stay aware of is that we need to start adding a key when we do a model. So particles moving at the same speed in random directions. So it doesn't say if it's a solid, liquid, or gas, so I'm just gonna the key here is that I'm going to call this a particle, and this is indicating the speed. So this is what this model is about. However, say there was a different type of model. There's two different substances, right? So if there was two different substances, I would use a different way to show there's a different substance. So this is, I would use, maybe this is a, so I'll call this maybe particle 1, and this closed one I would call particle 2. That way I can differentiate between them. And the speed, if they were moving the same speed, I would try to create an arrow the same size. But say this one was cold, so it's moving very slowly. Cold equals small arrows, okay, equals moving slowly. Whereas warm equals large arrows, which equals moving faster. Okay, so say I had another particle, and the particle is actually warm. So speed, so I'll make this larger. Okay, again I'm showing speed, and I'll make this one larger. So this model now is showing, it's not showing what this is saying, but it's showing something else, because I wanted to show you something else. It's showing that there is two different particles, particle 1 and particle 2, and they're not at the same speed. In other words, they're not the same temperature. There's some cold here and then some warm. That's what this model is showing. Okay, so third, we can show energy transfer by drawing arrows larger than the moving arrows from one region to another, or one particle to another. So let's see what this looks like. Okay, so this is going to be very similar to what I did, hot particles in contact with cold particles. So I would just, okay, so let's call this, I'm going to call this particle 1. I'm going to make the same particle. So it's the same thing. For example, ice in water is the same thing. Water is water, right? So I'm just going to call particle. And actually, I'm going to make the same ones. Particle is a particle. It doesn't matter if it's hot or cold. The only thing that's going to differentiate between them is the size of the arrow. Big arrow. Big arrow. So the arrows here is, we know that this is speed, and you can even be more specific and say this is moving slow and this is moving fast. So before I do the last rule, I just wanted to bring out those two examples. So what is the difference between those two? Okay, so we have particles moving fast and slow. The difference between them, and I'll give an example. Here is an example of you put an ice cube in water. Ice is made out of water particles, and water is made out of water particles. So they're both the same thing, they just have different temperature. In here, it's like, let me use an example, putting cold oil, cold oil in water. Okay, so it's different temperature. So two different substances and two different temperatures. Okay. The cold oil in water was a terrible example. It's just early in the morning, I can't think of anything else. But two different substances, that's what I wanted to say. So here we need to finish with the last rule, is that we need to show energy transfer. We show energy transfer with a big arrow, like this. And make the arrow different than the other one so you can really see it. And this big arrow, we call it energy transfer. It's just a way to explain heat transfer with all those models. Notice that the direction is extremely important. It's moving from high to low. Right? Remember the conversation we had right here? Heat always moves from hot to low. Since that the large arrow indicates that something is warm or hot, it's always moving from hot to cold. So those are the rules. Using those rules, I'm going to go through two examples with you guys. Most of the cases, I won't have pictures for you guys to create the models. I'll just say create a model of a cold and a warm, and you just need to draw the particles. But here, I wanted to use the pictures so you can have a better visual. So this is a cold substance. So there's two ways you can go about showing that the substance is cold. You can just put it in here. Doesn't say whether it's a solid or a liquid, so I'm assuming they're all solids. Although now this is water, so it's a liquid, so I'm going to load it. I need to space it out a little better. So this is going to be cold, so I'm going to make tiny arrows. Okay. This is a hot substance, so I'm going to, doesn't say it's the same or not, so I'm assuming it's different. And I'm just going to make the arrow for a few of them, and we assume that they're all the same, just because otherwise it would be impossible to create those big arrows. It would become a mess. We just need to show some of them. Let's create a key. Okay, so particle 1, particle 2. They call this particle water, so I'm going to say water. They didn't say anything about what this is. I'm going to say that this is slow, or I can just call it a speed. This is fast, right? Just to emphasize that this is cold, this is warm. When I put them together, what's going to happen is there'll be a heat transfer, so I can just show that here. There's a heat transfer. And eventually, after a while, now it's blurry. Hang on a second, let me just get this document camera just to focus. Okay, thank you. Document camera. What I need to show now is that they both reach the same temperature. And I'm showing this by creating the same size arrows. Okay. and then I'll put a couple water particles over here, and notice that I'll create the same size arrow. Okay, so this should be way longer. Okay. Slow, fast, and I put here equilibrium, or you can put medium. Okay. So in here there's no energy transfer because they're both at the same temperature. Okay, same thing. Same temperature. Okay, so important things, notice that I spaced out the liquid versus the solid. You don't have to put arrows for every single particle. Okay, just show me a couple, otherwise it gets too messy. Show me a couple, just to show me that you understand that the hot means it has a big arrow. Okay, and then show me the energy transfer. And then here show that the arrow is the same size. Okay, so this is drawing inside the particles. Inside objects, I mean. The other way that I've seen models done is by the zoom in method. What you do instead of drawing inside, which you can, doesn't have to, there's no right answer. What you do is you just create a zoom in of what it looks like. Just a zoom in here, and a zoom in here. Okay, so this is the system. Let me make this over here. This is the system. Okay, so you have a stove, and the stove is heating up the water. Okay, and we don't have to worry about, I mean, we can go on and on because the heat transfer goes from, technically, it goes from the metal and the stove, which probably came from some sort of fuel, natural gas or something, or electricity, right? Some sort of fuel generated electricity, and actually this heats up, and the heat transfers to the glass. This pan looks like glass. I'm not sure if it's aluminum or glass, but transfers to the glass transfers to the water eventually evaporates, and the heat of the water vapor transfers to the air around it. But this is too much. You don't need to worry about all of that. All you need to show me is from the stove to the water. Okay, so I would show the particles of the stove as a solid. Okay, and I would show the water. Obviously, the stove and the water are different, so you better show me different particles. And you show that the stove has a lot of heat. And you show me that the water is hot, but not as hot. So this is a case where they're not in thermal equilibrium, and they won't reach thermal equilibrium. The water will evaporate before that happens. So they won't reach thermal equilibrium. So the heat transfer obviously is from the stove to the water, and eventually to the water, from the water to the air, but you only need to show me this one. You need to have a key. Okay, I'll put here as water. Put here as stove particles, water particles, and then the smaller arrow, it's slow, large arrow is fast, and this means heat transfer. Heat transfer. Okay, the key here is not to make too messy. I do need to be able to understand your model, so try to keep it clean. You don't have to put tons of particles. You just need to focus on the main idea, which is that a solid, a liquid, or a gas? How fast are they moving? And what direction is the heat transfer? And make sure that you have a way that everyone can read your model. So that is the end of my notes. Let me know if you have any questions.